Hello everyone, here's a solution to that third example I gave you from last week where you had to solve for x and we were given that 2 to the x is equal to 4 minus x squared. So I first want to go through the sketch of this. So obviously it's not too terrible to sketch the graph of y equals 2 to the x, just an exponential function. Also, graphing y equals 4 minus x squared is a parabola that opens down. So here are two graphs. And now we, like our number 17, we have two points of intersection. In this case, one's positive, one's negative. So here, I'm going to let f of x equal 2 to the x minus 4 plus x squared. I want to bring everything over to one side. Imagine like it's set equal to 0, but call that f of x. Then our derivative, be careful here, remember the rule for 2 to the x, it's 2 to the x times a natural log of 2 times a derivative of x, which is just 1, and then plus 2x. So here's my Newton function that we're going to define on the calculator. And then I want two initial guesses here because I have two solutions. Now, based on my graph, it looks like x equals 2, or negative 2 rather, is at least a good first guess if it's not that exactly. So I'm going to let my initial guess x sub 1 equal negative 2. And please do this. Label them this way if you do have to find two separate answers. And then over on the right side, I could start with a 1.5, but I just chose to start with 1. So my second x value here, my initial guess is going to be 1. So I will let you pause the video at this point, and you could look over the number of iterations, what each decimal approximation comes out to be. And again, if you have any questions, please email me, let me know. All right, so today we're going to start section 4.6. This discusses something called related rates. So the examples, I'm going to do 3 examples right out of the book, problems 2, 4, and 8. All right, so this is on page 237. Number 2 tells us the radius r and surface area s of a sphere are related by the equation s is equal to 4 pi r squared. We want to write an equation that relates ds over dt to dr over dt. So we're actually going back to something we've discussed a while ago, implicit differentiation in a way, and parametric equations where we have this third variable time that is with everything is showing with respect to. So we're looking at the rate of change ds with respect to the change in time. So the change in surface area with respect to the change in time. dr over dt is the rate of change of the radius over, or the change in the radius over change in time. So it is the rate of change of our radius and then the rate of change of our surface area with respect to this third variable time. So I'm going to start with my equation, s is equal to 4 pi r squared. And then I simply take the derivative of each side. So the derivative of s with respect to time, there is where my ds over dt shows up. And then over here, I'm going to take the derivative of 4 pi r squared, again with respect to time, so over dt. So this ds over dt, I simply just leave it without the parentheses. And then when I go to take the derivative of 4 pi r squared, the 2 comes down, multiplies by the 4, so I get 8 pi r. And then just like with implicit differentiation, since I'm taking the derivative with respect to time, just like how we'd have to write a y prime after a y, instead of writing r prime here, I'm just going to leave it as dr over dt, because those are the terms they wanted us to leave this in. So this is it. ds over dt is now related to dr over dt. All right, let's take a look at number 4. In this problem, it tells us the power P in watts of an electrical circuit is related to the circuit's resistance R in ohms and current I in amps by the equation P is equal to R times I squared. 2 parts here. The first is how is dP over dt related to dr over dt and di over dt. So it's the rate of change of power, the resistance, and the current, all with respect to time. So just like the last problem, I'm going to start with the equation P is equal to R times I squared, and I want to take the derivative of each side. So here's my dP over dt. How does that relate to this derivative here? So the dP over dt is going to stay. And when I take the derivative of the right side, I have to use the product rule. So I'm going to have my uv prime. So that's going to be r times derivative of I squared becomes 2I. But then I is some function, so now I have to multiply by I prime, or di over dt, plus I'm going to have my I squared. Derivative of r is just going to be a 1, but then times dr over dt. And the only thing I'm going to rewrite is this 2. I'm going to put this out in front. So dp over dt is related to the other two rates of change in this equation. 2 times I times r times di over dt plus I squared times dr over dt. Now part B is asking, how is dr over dt related to di over dt if p is a constant? Again, I'm going to go back to the formula. P is equal to r times I squared. But if p is a constant, let's rearrange this. Let's solve this for r. So r is going to equal p divided by I squared, or we could write this as p times I to the negative second. And then I'm going to take the derivative of each side. So this is where I get dr over dt. And then that's going to equal derivative of p times I to the negative second over dt. So dr over dt. Again, p is a constant, so this is just going to become a negative 2p times I to the negative third, again, times the derivative of whatever I is equal to, so di over dt. We could leave it this way, or we could just put that I to the negative third. We could flip that, take the reciprocal. So we could say that this is negative 2p divided by I cubed times di over dt. Now all of these are going to play an important part. When we get to the next example here, you're going to see how understanding how to do this is going to apply to certain word problems. So with these word problems, I call this my 6-step plan. So number 8, when a circular plate of metal is heated in an oven, its radius increases at the rate of 0.01 centimeters per second. At what rate is the plate's area increasing when the radius is 50 centimeters? So we have two different types of rate of change here. We have the radius, how that is changing with respect to time. And then we're asked to find how the area is changing, the rate of change of the area. So again, I call this, we're going to use the 6-step plan. It's just one way to keep our work organized and remember all the steps that are involved to do this problem. So the first step is to just create a picture. Sometimes our pictures are very simple. Other times they're more elaborate, just like our optimization problems. And they're very useful because sometimes we need a helping equation. So in this case, I just have my circular plate that has a radius. Now this radius is increasing, so what's going to happen is the plate is going to increase in size. That means our area is also going to increase. So that's pretty much the picture that we're using to show what's taking place here. Now step 2 is I want to write out what we know, what we're given. We are given that the rate of change of the radius, so I'm going to use that dr over dt to represent the rate of change of the radius with respect to time. That's equal to 1/100th centimeters per second. Now because it's the radius is increasing, it's going to be a positive rate of change. All right, next, what are we asked to find? We are asked to find the rate of change of the area, so dA over dt when the radius is equal to 50 centimeters. So it gives us a certain point or an instant when we want to calculate this. Step 4 is we need an equation that relates area to radius. Well, the area of a circle is equal to pi r squared. That contains an area and a radius. The next step is to differentiate what we were just doing in our last two examples. We want to differentiate the equation with respect to time. So that means we want to find dA over dt, and that's going to equal d of pi r squared over dt. I'll just do this underneath. So we're still just going to have dA over dt. This will give us a 2 pi r times dr over dt. So there's our equation. Again, that's what we just practiced in problems 2 and 4. Step 6 is now to evaluate, because we want to find this dA over dt. So dA over dt is going to equal 2 pi. The radius, remember we wanted to find that when that was 50, so then that's going to be 50. And then dr over dt was 0.01. Right, and we can just calculate this. We know 2 times 50 is 100. This is 1/100th of 100 is 1. So dA over dt is equal to pi. And we're going back to centimeters because it's area, centimeters squared, or square centimeters per second. And there is the rate of change of our area when our radius is 50 centimeters. Okay, so your assignment for today on page 237, try 1 through 9 odd. Looking at AP practice problems, page 5, number 14. This one is no calculator. And then try another solving an equation using Newton's method here. This is e to the x is equal to 6x squared. Again, take this out to 12 decimal places and write out how many iterations it took for the solution to converge.